and
Hey, good evening, everyone.
release the video.
Yeah, release the Kraken here. All right. Let me get John on. John's
I'm
there.
here.
Oh, great. Well, good evening, everyone. This is Rich Ozer, and up here at the Shibose Basin Science Center, sitting in front of Nellie, our 36-inch research reflecting telescope. I'm here with Gerald McKeegan, and John Curry is joining us from home. And
And Gerald McKeegan would like you to release his video so you can.
I was wondering what was wrong. Hold on for
Yeah.
a moment. There we go.
All right. Start
And
my video. There we go. It's me.
great. All right. So our challenge tonight is to show you something before the humidity jumps to 85%. And what are we at right now?
We are at 81 right now.
All right. Well, I'm going to talk less and share my screen. And we're going to
Let's go.
We're going to look at the moon. That's right.
Yep.
Here we go. And you don't even have to wait for us to find the moon. We're already there in anticipation. So, Gerald, take it away and tell people what we're looking at.
Okay, well, you're looking at the northwestern part of the moon. The moon is waxing gibbous, almost full. It's going to be full, I believe, on Wednesday morning. So we still have a little bit of a terminator, the boundary between the dark and the light area. You see up to the left, that kind of a half arc that you see with a smooth area below it. That's called sinus iridum. And the big smooth area below that is the Imbrium Basin. And so we are looking at the northwest part of the sky. I'm going to kind of slew around here a little bit and maybe wander around elsewhere. Down here, this is the crater Copernicus right here, that big bright thing there that's in the middle with all those rays extending out of them. Those rays are caused by ejecta that flew out of that crater when the impact occurred. And as you can see, that ejecta has flown quite a distance, hundreds of miles. Off to the left of Copernicus, you see another crater that looks like just a little bowl way off to the left. That's Kepler. We'll move a little bit to the other side here, a couple of other craters. There's one that's right smack in the middle. It's a little hard to see. That's the crater Eratosthenes, named after the Greek philosopher who first measured the circumference. That's it right there. First measured the circumference of the Earth. His name was Eratosthenes, and he came up with a very ingenious way to measure the circumference of the Earth. I think it was around 300 BC. So, contrary to popular belief, they did not believe the world was flat back then. To the right of that, you see an arcing range of mountains. That's called the Epinines. And there are actually several mountain ranges. Those mountains are actually part of the rim of this huge impact basin, which is the Imbrium Basin. And as you can see, that the mountain range arcs up, and as you get farther north, the name of the mountain range changes. The lower part there is called the Epinines. The part in the upper right here is called the Caucasus. And then way up north, up in that region here, you see the Alps. And then you see that round crater up there with the smooth floor, that's Plato. And so this is the northwestern region of the moon. Go on over here, just below the big smooth area right here, that's Serenity, the Sea of Serenity. And then coming down even farther, this darker area, that is Tranquility. That's where the Apollo 11 landed. Coming over here to the right, you see a round, smooth, dark area. That's Mare Crisium. And then in between Tranquility and Crisium, you see a bright crater with kind of a butterfly pattern of ejecta. That's called Proclus. Proclus is an impact crater that was caused by a very shallow angle impact, asteroid hitting the moon at a pretty shallow angle. So, working my way around here, a few other places here. By the way, you notice that Tranquility, the floor of Tranquility, if I get in the right direction here, there we go, is darker than the floor of Serenity.
Yeah, I was just noticing that. What's that
In
about?
fact, it's darker than any of the other impact basins. And it turns out that's because the lava that filled the Tranquility Basin is richer in titanium than the lava that filled these other basins. All of these dark regions that you see on the moon are what we call mares or seas, and they are actually large basins that filled with lava about 3.5 billion years ago or so. You had some very big impacts at that time, impacts that were so strong that they cracked the crust of the moon. And 3.5 billion years ago, the moon still had a molten interior. And so lava oozed up from the interior, I should say magma oozed up from the interior through those cracks and erupted onto the surface where it became lava and filled these basins with this dark material. And the thing that distinguishes Tranquility is the higher titanium content versus the rest of the basins. So that's Tranquility. Wander around here. Believe it or not, our humidity has gone down, Richard.
Oh, good.
So we must be getting lucky here.
Yeah, I thought our next show was going to be showing everyone closing the roof of the observatory. So.
All right. So we're going to come on down here, I think. Get down here and see Gazende, and actually this was Gazende right there. That round crater you see just off to the. Let me get that one. Yeah, that's it right there.
Right there.
Yeah.
And anything to say about this little one right adjacent to it? That's really interesting.
Hang on a second here. I'm cheating tonight.
It's okay. We don't expect you to know them all by heart.
Yeah, well, tell that to Chuck Wood,
your professor.
My professor when I got my master's degree. He's one of the world's leading experts on lunar geography, and he might have a different opinion. Okay, that's actually Gazende A. That little one is Gazende A, and the main one is Gazende. Below that is Mare Humorum. And then let's see, where else are we going to go? Oh, yeah, we need to go down to Tycho.
I do want to mention something right here in this view. One of the reasons we like looking at the moon when it's not full is you're able to see this kind of relief here at the very edge because the mountains and craters are casting shadows. And so we're able to actually get more of a three-dimensional viewpoint of what the moon looks like. But during a full moon, when the entire side of the moon facing us is fully illuminated, it's really very flat. We don't get any of that sense of relief. You can see here that there's a mountain area and a shadow right behind it, and you really get kind of a nice 3D effect on when it's in a partial phase.
Right. And one of the other things we should point out is we do have a little bit of wind going on tonight, and we have some smoke in the air. So our image is not perfect. And if you look at the image over to the right, which is a close-up of just a small section of the main image, you can actually see how it's going in and out of focus. And that's because of turbulence in our air. The turbulence causes the density of our air to change moment by moment. And so you'll get moments of clarity and then moments of fuzziness. And that is what astronomers call seeing. And the less of that we get, the better we like it.
Hey, Gerald.
Yeah.
Sandra wants to know, how do we know about the titanium levels in Tranquility?
Well, remember, we had astronauts go there
Mm-hmm.
and they took samples of Tranquility. So they were able to bring those samples back and they were analyzed. We had astronauts go to other basins as well. And so we have samples from several of these basins. And so we can actually tell by analyzing those samples what the composition is. You can also, using spectroscopic techniques, looking at reflected light off of the moon and analyzing its composition or its the absorption lines in it, you can also make some determination about the content as well. But direct samples from the site is the best way, and we have those. Okay, I was going to head on down here a little bit more south. You see a bright ray there, and it comes back to a very bright crater that you see down at the bottom of this image right now. That bright crater is Tycho. For you folks who might be fans of the movie 2001, that's the home of the Tycho anomaly. Tycho is a relatively young crater. We think it may be actually less than 100 million years old, which makes it young. Most of the craters we see on the moon are much older than that. And Tycho has these huge rays that extend in all directions out of it. There are rays that actually extend 1,000 miles from it. So that tells you it was a pretty powerful impact, and it threw a lot of material up. The moon has a much weaker gravitational field than the Earth. It's only 1/6 of the Earth's gravity. So if you throw stuff up into the air, it's going to go a lot farther. And we see that with the rays from Tycho. Let's see, what else we see here?
We got a question from Marianne. Hi, Marianne. How are you? Yeah, there's no way to avoid the turbulence in the image. That's caused by atmospheric seeing. The easiest way for us to avoid turbulence in the image would be to take the entire observatory and move it into outer space.
Yeah.
And then we would not have any turbulence at all.
Yeah. You see kind of an elongated crater right at the terminator line there. That is actually called Shiller, and we think it's actually two craters overlapping each other. So let's see, where else can we go here? Let me cruise around a little bit. We're getting into the Lunar Highlands. The southern part of the moon is much more mountainous than the northern part. There are fewer basins there, so it's much more mountainous, much older terrain. So we're getting into that area here. Let's see if I can figure out where we are looking right now. Okay. The smooth area right smack in the middle, that's called the Sea of Nectar. And then just up above and to the right of that is the called Mare Fecunditatis. I can never say it.
Fecunditatis, yes.
Thank you. And there's a little crater that's just off to the left here, just to the left of Nectaris. I'm not sure how well we can see it. Let me.
Which one are you looking for?
Well, it's up a little bit farther. Yeah, it's not showing up very well.
Okay. I think was it
yeah,
right there?
It's Theophilus.
Yeah.
Yeah, I wanted to show.
It's interesting looking, but it really doesn't show up well tonight. Yeah.
Yeah. So Theophilus is there. Theophilus is a round crater with a very pronounced central peak. And a lot of craters on the moon have these central peaks. They're called rebound peaks. So when larger asteroids hit the moon, they produce bigger craters. And when a crater is beyond a certain size, you get rebound peaks. The impact compresses the crust below the center of the crater, compresses it, and also throws material out up onto the rim of the crater. And when the impactor disintegrates, the compressed ground at the center of the crater rebounds back up. At the same time, all that material that was thrown up onto the rim slumps back down. And those two forces combine to produce that central peak that you see in larger craters. Smaller craters don't have a central peak. They're more just like a bowl. So that's one of the ways you can distinguish big craters from little craters, and more forceful impacts is whether or not you have that central peak.
John, you want to go over some of the questions that have been
Yeah, we've got a
asked?
couple of questions. One was about that turbulence, quote, turbulence again. Why can't we use adaptive optics to fix that? Yes, we certainly could, but that's very expensive.
Yeah, you have to get us a
Don't have
grant.
Right.
In which case, we'd be happy to try it out.
Yeah, donations gladly accepted.
Yeah.
And I've got a couple. They're scrolling off, and I can't.
Well, actually, I want to say something. I want to say something else about that. Adaptive optics would be really great here, but the problem is we're really close to an airport, and part of the most adaptive optics systems involve shining a very bright laser into the sky, and I don't think the FAA would appreciate that from coming from the Oakland Hills. They barely get away with it from the Lick Observatory, but that's one of the problems of using adaptive optics. Although there are some other types that we would be able to use that might.
Yeah, one of the ways to get away with it at Lick is by having a guy stationed outside while they're using the adaptive optics laser. And that guy's sole job is to watch for airplanes. And if an airplane flies overhead, he tells them, turn off the laser real fast.
He actually has a button that he can press that stops it.
Yeah.
But it's a hell of a job. Not
Hey,
really
John,
much fun.
John, you're hired.
Thanks.
So we wish we could, but unless somebody wants to make a very big donation, probably isn't going to happen.
Also, a question that came up about, do we know much about the altitude of the highest mountains and the lowest points on the moon?
Yes, the altitude difference is about the same as it is on Earth. So, on Earth, we have peaks that go up to about 29,000 feet. And the peaks on the moon are just about the same. Most of those craters are 3,000 or 4,000 feet, the big ones that you see. And of course, smaller craters are not so deep. But the peak heights are, for the most part, similar. There are a few that are a little bit higher than on the Earth, but most of them are similar in height. It's just that you have a lot of places where it goes from very high to very low very fast because of all those craters.
Also, what is the biggest crater on the moon? Letty wants to know.
Well, I would say the Imbrium Basin, which is what we're looking at right now, is actually the biggest crater. We call it a basin because it is so big. But if we could zoom out, we could see that
it would form a circle.
Yeah, it forms a circle.
But you don't see that from this image very well.
In fact, the Imbrium impact nearly destroyed the moon. It was a big impact on the moon. And when that occurred, the shock wave of that impact reverberated outward in all directions and went all the way around the moon and converged on the backside of the moon. And if you look on the backside of the moon, exactly opposite of where the Imbrium Basin is, you see all this very jumbled terrain, which is where all of the shock waves that went outward from the impact all converged on the opposite side of the moon. So it's a pretty cool effect.
Gerald, one of the questions that was asked also is someone was trying to get a sense of image scale and magnification here. And I was kind of just off the top of my head thinking we're magnifying about 300x. Is that your sense?
Yeah, about 250 to 300, something like
Right.
that.
Okay.
Yeah. So this is about what we would see if we looked through the telescope eyepiece. If we put an eyepiece on and look with our eye, the view would be a little bit wider, but not a whole lot wider than what we see right here. And your eye has much greater dynamic range. So a lot of things that look kind of blended in this image would stand out more sharply if you were looking through the eyepiece with your eye instead of with our camera.
And with Nellie, it would be a very, very bright image too. Almost painful
Yeah.
to the eye if we don't.
It's kind of it's like if you're looking at the moon through Nellie, you want it to be the last thing you look at while you're up here at Chabot on a Friday or Saturday night when we're doing public viewing again, because your night vision will be obliterated by looking at the moon through a telescope this size. So
yeah, fortunately, we only look with one eye at a time through the eye.
Yeah, that's right. You have your moon eye and your deep sky eye.
Divi would like to know if there are any moon quakes on the moon.
Yes,
Great
there
question.
are. Yes, there are. We actually have several seismometers on the moon left there by the Apollo astronauts. And there are little moon quakes, which suggests that there may still be some activity in the interior. Now, part of that may just be because the moon is slowly shrinking. As the interior cools, it shrinks a little bit. And so we think that's one reason for the moon quakes. There is some indication from some of the analysis that has been done by those seismometers, also some spacecraft that have orbited the moon to measure precisely its gravitational field. There is some suggestion that there may still be a little bit of volcanic activity, I guess you'd say, in the interior. Also, occasionally, there appears to be some volcanic activity on the surface. In fact, if you look up to the very upper right-hand corner, right near the limb there, you see a crater that's almost in the shadow. That region there, that crater is called Aristarchus. And that region is suspected to be slightly volcanic.
Huh.
The reason they suspect that is because I'm having a little trouble here. Bear with me.
And you meant upper left corner, right? You meant
upper left. Yeah, I'm sorry.
Yeah.
That's
upper
okay.
Left corner. And you're talking about this crater here where my cursor
is?
Right,
exactly.
Okay.
Right.
All right.
Right. So what you can't see is there's actually kind of a mound that just inside the shadow part. There's a mound there, and we know that's a volcanic mound because we can actually see where lava has flown. There's kind of a sinuous little channel where lava has flown out of the crater, very small crater at the top, and it's a caldera. So that is definitely a volcano. The reason we think that there may still be some activity there is that every once in a while, astronomers will report seeing some brightness there, like a bright flash or maybe some smoke. It's very subtle, and it's always so brief that by the time they say, "Hey, everybody, look," it's not there anymore. But it's consistently over the years, people have spotted something there, some sort of transient event, that may be, in fact, the last gasp of a volcano.
That's
So,
really interesting.
yeah.
And I didn't think there was enough heat generated
Well,
by the moon's geology to create that.
well, that's what the assumption was, and has been for quite a while, that it's just cooled off enough at the interior that you wouldn't get any more volcanic activity. But every once in a while, we get little hints that maybe there's still a little bit of it left.
Yeah, Mark would like to know, how do tidal forces from the Earth affect the geology of the moon?
Well, one thing it does is it's slowly flinging the moon away from us. And this is kind of I'll try to describe it. It's a little bit of a hard concept, but as the moon orbits around the Earth, it takes about 4 weeks for the moon to make one orbit around the Earth. But the Earth is rotating beneath the moon once every 24 hours. The moon's gravity pulls on the Earth, and the Earth's gravity pulls on the moon. The moon's gravity pulling on the Earth combined with the sun's gravity pulling on the Earth causes tides on the Earth. And you can think of tides on the Earth as being a slight bulge in, it's mostly the oceans that are bulging. But because the Earth is rotating faster than the moon is orbiting, that bulge is always slightly off line. If you imagine a line going from the center of the Earth to the center of the moon, that bulge is not perfectly lined up on that line. It's slightly off. It leads it slightly. And because of that, the gravitational pull between the Earth and the moon is slightly off center. It sort of is a little bit ahead of that line connecting the centers of the two objects. Because of that, the moon is being slightly accelerated by the Earth's gravitational pull because of the tides, and that is causing the moon to slowly drift away from the Earth. The moon is receding from the Earth at about 1 inch, 1.5 inch roughly per year. So the tides on the Earth definitely affect the moon. And of course, the moon is what creates the tides on the Earth. So it's a kind of a mutual reaction. So the moon will slowly drift away, but that whole process actually results in an exchange of energy. Because of this process, we're giving up a little energy from the Earth's rotation to accelerate the moon so that it moves away from us. So the Earth's rotational speed is ever so slightly slowing down as the moon's orbital height increases. So we're exchanging energy between the Earth and the moon. You have to conserve energy. So the only way you can do that is to give up a little energy on the Earth and give that energy to the moon. And it takes it by increasing its altitude. So
kind of like an ice skater extending their arms to slow down their spins.
Right. One of the interesting things is right now the moon's distance to the Earth, the center to center distance, is about 239,000 miles on average. It varies by quite a bit, actually. But billions of years ago, the moon was much closer to the Earth. In fact, I've read some things that the moon may have been as close as 20,000 miles. So basically 10 times closer than it is now. So you can imagine the tides we had back then. So what's going to happen is as the moon recedes away from the Earth, the tidal pull of the moon on the Earth will decrease, and eventually it will reach a point where there's just not enough exchange anymore to accelerate the moon anymore, and then it will stop drifting away from us. Of course, by
it'll
then,
reach some maximum.
Right,
as a
but
result of
that's
this of the physics of what you described.
right. But you're
And
talking
we'll have
millions,
millions of years, right?
billions of
Yeah,
years.
yeah.
Yeah.
So the related question is what will happen to the tides? Well, they would be reduced to
Right.
some degree.
Right.
We will always have tides due to our
The
orbit
sun
around
as
the,
well.
our orbit around the sun. That's correct.
Right.
So, but not like we have now. I'm just trying to imagine what the tidal forces would have been like with the moon 20,000 miles away.
Yeah.
I mean, that's just hard to
Surfing
also,
would be great.
yeah, surfing would be great. The view, I mean, imagine what that would look like in the night sky. I mean, if you look at the moon now, it's the size of a pea, and it would just be this immense round white ball in the sky, 10 times the size of what you see now. It's hard to imagine what that would look
Yeah.
like.
One of the interesting things, we'll get a little philosophical here for a second. Back then, of course, the moon would be so close that when it passed in front of the sun, it would be huge compared to the sun. And the sun actually was smaller. 3 billion years ago, the sun was a little bit smaller than it is today. So the moon would be just huge compared to the sun. Even a billion years ago, the moon was still closer and the sun was a little bit smaller. So when the moon eclipsed the sun, you wouldn't get those perfect eclipses that we get today, where the moon is just the right size to perfectly overlap the disk of the sun. A billion years from now, the sun will be larger than it is and the moon will be farther away. So you will never get that perfect total solar eclipse after that. So, a billion years ago, there were no human beings on the Earth to appreciate a perfect total solar eclipse. And a billion years from now, there will be no human beings on the Earth to appreciate the fact that we no longer have.
Or get them in while you can.
So,
Right.
So the coincidence of the moon being just the right size to perfectly overlap the sun coincides with the existence of human beings on the Earth.
Oh, that is cool. If we or some other species are spacefaring, and a billion years from now, all you have to do is take a rocket out into space and get a little bit closer to the moon, and then you'll get that perfect eclipse again.
Arrange your own eclipse.
That's right.
Well, Gerald, this one goes back to your lunar geography class. How many total craters are there on the moon?
How many total craters on the moon?
Yeah.
We don't have enough fingers to count them.
That's right.
One of the great thing is the more you zoom in, the more craters you see. There are craters on top of craters on top of craters. So they're just literally, there are billions of them, way too many to count. Any rock that hits the moon, no matter how small, is going to produce a crater. The moon has no atmosphere. It has no plate tectonics or oceans or rivers or anything like that. No vegetation. There's nothing to wipe out a crater. And there's nothing to cause a small meteor to burn up before it reaches the moon. So even tiny rocks hit the moon and produce craters. So you can just keep getting closer and closer, and all you'll do is see more and more craters. So too many to count.
Too many to count.
Yeah.
Okay. Well, one more question. Why did we choose the Sea of Tranquility as the first lunar landing site?
One reason was it was close to the lunar equator. The first couple of landings that they made, they wanted them to be close to the lunar equator because it would take less energy to get a spacecraft to land at the lunar equator. The farther you get away from the equator, the more energy it takes, the more maneuvering of the spacecraft. And because that first mission, they wanted to keep things at a minimum, they chose a site that was close to the equator and they wanted it to be a relatively smooth site so that they weren't dodging rocks and dodging mountains and things like that. Boy, the conditions are getting really bad here, aren't they?
Yeah, they are. Well, you know what?
Yeah.
The temperature just jumped like
Yeah,
7 degrees.
Yeah, the
I was
humidity's
sitting
going up
here.
again.
Yeah,
Yeah.
we're up to
Yeah.
82% now. So
Yeah.
so anyway, it was they wanted a place that was interesting, that had some interesting rocks to pick up. They wanted it to be not very challenging for landing, so they wanted it to be someplace smooth, and they wanted it to be close to the equator. So for those reasons, they chose the Tranquility Basin, or the Tranquility Sea to land.
And of course, it looked a lot smoother from Earth than it really was.
It did. One of the things that they discovered as they were coming in for a landing, and Neil Armstrong was looking out the window at the spot where he was supposed to land, and it was all covered with boulders. So he had to take control and fly the LEM almost 5 miles to find a decent spot to land, which caused all kinds of confusion because they didn't know where he was. They couldn't find him because he didn't land where he was supposed to land. It took him a while to figure out where he was.
Jose, Gerald already gave a pretty lengthy explanation on the reasons why the moon is moving away. One of the neat things about broadcasting to Facebook is you can go back and replay the video. And if you hit about 15 minutes into the presentation, after it started at 9 o'clock, you'll get the full explanation of that. So that'll be in the videos section on our Facebook page after the presentation is done tonight.
So Richard, our humidity is getting higher here. We're up to 83%. So how about if we take a quick look at Jupiter?
Okay, sounds good.
All right.
We'll look at a fuzzy Jupiter probably, but let's look at it.
While you're doing that, Gerald, there was one question that I let slip by. It was when we were talking about the seismic activity on the moon. Will there be enough seismic activity to erase the astronauts' footprints that are up there?
That's a great question.
Not for about a billion years.
Yeah.
Okay.
There is just no weather. There's nothing to erode that. So the only thing that's going to erode those footprints is the slow, continuous pelting of micrometeorites hitting the moon and slowly, very, very slowly eroding them down. But it'll take millions of years for that to happen. So,
or possibly new footprints from somebody else walking on top of them.
Well, technically, the Apollo sites are now, I think they're called historic sites or something like that. So you're not supposed to go there. So don't tell Elon Musk.
All right.
Well, there's a fuzzy Jupiter. Not a very good image.
No, not a good image at all. But it is what it is. You can barely make out the cloud bands, and what I'll do is we were able to see 4 moons earlier, but we can only see 3 now because one of them went behind the planet. Io went behind at about John, you had said like 9:08 or something.
9:08, I think, was the time that it went behind. Yeah.
But if I boost up the exposure to some ridiculous amount here, let's go up to 6400 ISO. We're able to see Europa, which is right here where the cursor is, and Ganymede. And Callisto's out of view. Gerald, if you want to try slewing to the left, maybe we could see Callisto as well. You want to give that a shot? I don't see it. Where's Callisto? There. Callisto is right here. Let me see about brightening this up even more.
Brighten that because I can't see it. So
there's I'm gonna go even brighter. Make it ludicrously bright here. All right.
The brightest one is Ganymede. Ganymede is the biggest moon of Jupiter. Yeah, now I can see Callisto.
Might be hard for people on Facebook if you're looking with like a phone, but if you're on a computer, you'll see them.
Yeah, so the brightest moon, there's 3 moons you can see. Right in the center is Ganymede. To its left, a little bit fainter, that's Europa. And to the right, pretty faint, is Callisto. Ganymede is actually the largest moon in our solar system. So not only is it Jupiter's biggest moon, but it is the largest moon in our solar system. It's almost 3,000 miles in diameter, whereas our moon is only about 2,000 miles in diameter.
I never realized that. I always thought just by name that Titan was, and I had that misinformation rattling around in my brain for a long time.
Well, we can't see the bands, but Richard, I'm gonna, if I can share my screen here, I got a couple.
Oh yeah, you've got a great set of photographs to show.
Yes.
So yeah, go ahead and do that.
So
I'm gonna stop my sharing, and it's all yours.
Okay. Where is it? There it is. Okay, so there's a spacecraft orbiting orbiting Jupiter right now. It's called Juno. It's a joint project between NASA and the European Space Agency. And they put together a series of images, and I'm going to share them with you here. So hopefully this will show up. So here's one complete rotation of Jupiter. And you can see there's a whole lot of stuff going on there. So we'll stop that, and we'll come in even closer. All right, so there you see an even closer view. There's a lot of turbulence in the atmosphere of Jupiter. Jupiter is huge. It's 88,000 miles across, so it's 11.2 times the diameter of the Earth. It's a gas giant, so it's a big rotating ball of gas, and some of that gas is pretty dense as you get down farther into the atmosphere. It's pretty dense. Its rotation rate is such that a day on Jupiter is only 9 hours and 50 minutes long. So at the equator, it's rotating really fast, and that creates a lot of turbulence in the atmosphere. Now, the cloud tops, when you look at an image like this, it looks like they're all flat. They're just swirling, but it's more or less flat. But if we zoom in even closer, yet another image here, we can see that it's actually very turbulent, and the clouds are not all the same height. We get like thunderheads in the atmosphere of Jupiter.
Well, judging from this picture, it's not like thunderheads. They are thunderheads.
Yeah, they are. Yeah, there's a tremendous amount of friction because of all that turbulence, and there's just lightning flashes all over the place. When you look at the dark side of Jupiter, it's just little flashes of lightning all over the place. So it's pretty spectacular.
So there's really two main forces contributing to these storms and cloud patterns. You got the rotational effects causing all of that atmospheric turbulence, and you also have upwelling because Jupiter is a gas giant and it's extremely hot towards the center of the planet. And of course, heat rises, and you get, just like you get upwelling in our oceans, which mixes what's at the bottom of the ocean with what's at the top of the ocean. It's part of the whole food chain cycle here on Earth. You get a similar effect in Jupiter with this giant volume of gas, with the hot gas moving up and the cold gas falling back down and getting heated up and cycling through that way.
Right, and there's quite a bit of turbulence, and you get a similar process. You get water droplets forming down farther in the atmosphere. They become ice crystals. They rise up because of updrafts, get carried high up into the clouds. they accumulate a layer of ammonia, liquid ammonia around the ice crystals, and eventually it becomes so heavy it begins to fall, just like the process that causes hail here on Earth. And it falls and it sheds all that ammonia and a lot of the ice, and rinse and repeat. Very similar to what goes on the Earth. That's one of the cool things about studying other planets. So we often learn a lot about processes on our own planet by studying them on other planets where they happen in a much more pronounced way, a much less subtle way, and so we can better understand how things happen.
Ginger would like to know what gases are there and are they toxic?
Yes, they are toxic. Most of the gas on Jupiter is actually hydrogen, but there's a lot of methane, there's ammonia, and of course, there's water vapor. And there are some organic compounds. Methane, for example, is an organic compound. It's a combination of lots of different gases, and some of those gases are in fact toxic or flammable, as the case may be.
And the question that we get a lot, is there a layer of liquid somewhere deep in the atmosphere of Jupiter toward the center?
If you go deep enough, the pressure is so high that the gaseous hydrogen turns into a sort of liquid state, but it's such that the electrons become free flowing, and that makes the liquid hydrogen under that high pressure. It makes it a conductor of electricity, and so we think we say that things that conduct electricity are metals. So the term for it is liquid metallic hydrogen. And that's deep down, it reaches that liquid state. And we think maybe at the very core, at the very center of the planet, there may be an actual solid rocky core. There's still some debate about that, but there's some evidence to suggest that.
That's a very strange state of matter. I mean, liquid hydrogen here on Earth, when we produce it ourselves, is at extremely low temperatures. And I'm having a hard time getting my head around the idea of superheated liquid hydrogen. Now, are those the electron flow you were talking about? Is that contributing to the magnetic field effects?
Oh yeah. The magnetic fields on Jupiter are just very dynamic.
They're off the charts. Yeah.
It's crazy. It's one of the problems that you have when you design spacecraft to go to Jupiter is you have to account for this tremendously strong magnetic fields.
Leslie would like to know if the images, these Juno images, are true color visible wavelength images.
No, they are the Juno colors. So a lot of them are actually not in the visible spectrum, and so they assign colors to them. So I think a lot of them are in the infrared spectrum.
Infrared, yep.
So they're assigning colors to them, which can be pretty interesting. One of the neat things is that you assign different colors to different wavelengths. You can assign colors that contrast quite a bit to wavelengths that are relatively close to each other. So if you could see in that part of the spectrum, you'd see two areas that to your eye would seem just subtle differences between them. But by assigning dramatically different colors to the two wavelengths, you see the contrast between them much, much more clearly.
One of the things I'd like to point out related to that is since we're studying these storms that are caused by thermal differences, then there's nothing better than an infrared telescope to tease apart the details of those cloud formations and to actually penetrate the upper cloud layer to see what's going on below by looking for hot spots that are only visible in the infrared. And one of the interesting things about the upcoming James Webb Space Telescope, which is a giant infrared telescope, is that its first mission is going to be to point it at Jupiter. And that's partly a calibration run to get the telescope working properly. But it's also a great piece of science because they'll be able to look at these cloud formations from the new telescope and gather more data about them.
James Webb Space Telescope still slated to launch next year. In fact,
Next year, hopefully, knock on wood.
It always seems to be next year.
Yeah, it's like nuclear fusion. It's
well,
always
they just completed some of they just completed some of the vibration testing. You know, they have to test it to make sure it will withstand the vibration of launch, and they were just did that here within the last week or two, and it successfully passed. So
that's good.
That's one more thing off the checklist. You know.
Yep.
Well, this is a question that I'm not even sure I can pronounce this right. Have you seen Fujiwara interactions of vortices on Jupiter?
I have no idea.
I don't know. I don't even know what that is.
Yeah. You've stumped the stars.
Okay, so Gerald, Debbie is pointing out that, or she's suggesting that picture of Jupiter's clouds with the lightning was not a photograph, but an artist's representation.
Yeah, I told you that a while ago.
Oh, okay.
It's a blend of a photograph and a
got
artist.
it. Some things were added. I see.
Right.
I see. Thank you, Debbie.
Well, the humidity's gone down again.
I'm just a little slow on the uptake.
We're hanging in there.
What's it at?
81 again.
81 now.
Oh, okay. Well,
yeah.
We can go over to Saturn again.
Yeah, might as well. Where is it? To the left, right there. All right.
Yeah, the seeing improved
go back
a little
to
bit
your
too.
live view.
Yeah. I will in a sec here.
Yeah. Make sure we got it all centered up here.
Stand by.
I see it
materializing.
I see
it's
it
down there at the bottom. For 1600.
pretty fuzzy.
Yeah. Yeah, very fuzzy.
Almost red from the smoke.
Yeah.
Yeah, that's the other issue is the smoke.
Yep. So our conditions are about as bad as you can get tonight.
Yeah.
Right on the cusp of too much humidity, smoky air, and terrible seeing.
This is about almost as bad as when Galileo first saw Saturn.
It's not that bad.
Galileo, when he had not a very good telescope, and when he first looked at Saturn, he couldn't figure out what those appendages were on either side. And in his notebook, he drew it as if it was a round ball with handles on either side.
Well, didn't he call it planet with ears?
Yeah, that could be. I don't remember. Yeah.
You don't remember? You were good friends of his, weren't you?
Yeah, that's right.
Yeah, but after he went under house arrest, I pretended I didn't know him.
That's right. That's right. You gotta protect yourself.
Yeah. Any pictures you see of me and him standing next to each other, I take lots of pictures with lots of people.
So something to talk about. Talk about the cycle of observing Saturn. That's always really interesting.
Yeah, Saturn takes 30 years to orbit around the sun actually slightly less. It's 29 and a half years, I guess. And its ring system, its equator and its rings are tilted slightly at an angle, so they're not perfectly. The poles of the of Saturn are not perfectly up and down or perpendicular to the direction of its rotation. It's tipped a little bit, just like the Earth is tipped a little bit. And because of that, the rings are tipped a little bit relative to the orbit of Saturn as it goes around the sun. But the direction that they point out into space is always the same. So as Saturn orbits around the sun, our view of it changes. The tilt of the rings appears to change over time, and it's simply because we're looking at them from a different angle. And what happens is we see the rings tip a whole lot, and then slowly the tip decreases and decreases and decreases, and then eventually we see it edge on, and the rings basically disappear. And then it continues to tip, so we see the other side of the rings, and it goes farther and farther and farther, and it eventually reaches a maximum. And then it goes back again in the opposite direction, goes edge on again, and then reaches its maximum tilt in the other direction. So one complete cycle takes 30 years. And so every 7.5 years, it reaches the point where we see it edge on. So that's pretty cool.
Yep. So we're getting pretty much to the maximum.
Actually, we
Right around
already
now. Yeah.
already reached the maximum, and
Yeah.
it's starting to go back again.
Yeah.
So in about
I gotta get my viewing in to see the gap in the rings.
Yeah, so in about 6 years, it'll be edge on.
Yeah, one of the when you have a visual instrument and you are enjoying views of Saturn, one of the things to try to look for are the Cassini Division and the Encke gap, or the Encke Division. And on a perfectly clear night, you could see those gaps in the ring. But of course, that becomes harder and harder as it becomes more and more of an edge-on view.
Yeah, I just rethought what I just said, and I didn't say it quite right. We see it edge on every 15 years.
15 years,
Yeah,
yeah.
it takes 15 or 7.5 years to go from edge on to full tilt.
Yeah, that makes more sense.
Yeah.
Thank you.
Yeah.
I was trying to think about the last time I saw it edge on, and I was saying, boy, it seems like it was longer ago.
Yep. All right. Well,
Yeah, Alina wants to know, where are Saturn's moons? Well, the seeing is probably just not good enough to see any.
Yeah.
Well, we could try, and the way to see, since we're using a camera and not our eye, what we can do is try bumping up the exposure to see if anything is popping out. And I don't see anything.
Yeah.
You may be very, very right, John, that we're just not seeing it tonight. I've got a maximum exposure right now. Huh, okay. So much for that.
It's that black dot over to the left.
Yeah, the red dot. Yeah, we were making jokes about the red dots. Those are the characteristics of my camera. I have 2 hot pixels, poorly positioned in the field of view, and not to be confused with anything real.
Yeah, it looks like Titan, one of the brightest moons, is a way out, so you're probably not far enough out.
Is it east or west, John?
It looks like, well, I'm not sure whether.
Well, we could try one way and then the other.
I think it's west according to what I'm seeing here, but I'm not sure.
Yeah, I don't see it.
Yeah, I don't see it.
Go the other way just in case.
It looks like it's quite a ways out. I would say at least about 6 ring diameters out.
I'm not seeing it. I'm not seeing it at all. Yeah, we might have to take longer exposures in order to catch that tonight.
Yeah.
Oh well.
Come back. There we go. Well,
All
I
right.
doubt if we're going to be able to see any deep sky objects.
No,
today.
I don't think it's a good night to try that.
Yeah.
There was a question about how much we would weigh on these gas giants.
On Jupiter, if you had a platform that was right at the top of the cloud tops, you'd weigh about 3 times your normal weight. It has a whole lot more mass than the Earth does, but because it's so much bigger, your distance from the center of mass is greater than the distance to the center of the mass on Earth. So the farther away you get from the center of mass, the weaker the gravity is. So, not wanting to do any math here because I'm sure most of you would be thrown, or a lot of you would be thrown by any equations that we threw up. Just be aware that the force of the gravity is directly proportional to the mass and inversely proportional to the square of the distance between you and the center of mass. So as that distance increases, the gravitational force decreases, not directly. So if you double the distance, it's not half, it's 1/4. If you're 3 times the distance from the center, it's 1/9. So that's why even though it's so much more massive, at the cloud tops, it's only 3 times the gravitational pull.
Catherine says she likes math, so good for her. There's also a question about the rings. Could the rings possibly break if a comet hit them?
Well, the rings are not solid. All right, that's the first important thing to know. So they wouldn't break. The other thing to know is that comets, although they're very spectacular in the sky, their nucleus, their cores, are not very big, right? So if a comet impacted Saturn's rings, there would be some localized disruption of the ring, and it would probably put on a great show, but it wouldn't have a permanent effect on the ring, because the ring consists of billions and billions and billions of tiny particles and ice crystals, and the vast majority of them would be unaffected.
I think I've read that the rings are not necessarily a permanent feature anyway. They may eventually go away.
That would be sad.
Yeah, me too.
Yeah. Well, that's an interesting thought too. The ring. I don't know if the ring is made of comets, but comets may have contributed to the material in the rings.
Yes.
What is more likely is that the pieces or material from Saturn's moons have made a major contribution to the rings. There are ice volcanoes on some of Saturn's moons, and they're spewing all kinds of material into orbit around Saturn. And Gerald, if you have more to say on that, that would be.
Yeah, if you'll allow me to share my screen here for a second.
Sure. Yep. Let me stop my share. You go for it.
There's a close-up of the rings taken by the Cassini spacecraft. And you can see that there's actually many more rings than you realize. What looks to us from the Earth, looking through our telescopes like one big ring, actually turns out to be hundreds and hundreds of little rings all stretched out. Got another image here.
And here's what I was talking about. You can see the Cassini Division is that big dark area.
Can you see my
right
cursor?
There? Yeah. Yep.
Yeah, this is the Cassini Division. And you can just see how there's all these little rings within the bigger rings. And the closer you get, you see even more and more individual streams of ice particles. As you get closer to Saturn's over here just out of the frame. The closer you are to Saturn, the faster you have to orbit. So particles at this part of the ring are orbiting much faster than particles in this part of the ring. And so that creates a shearing effect, which causes the rings to actually be a bunch of little rings rather than, a few big rings.
There were a couple questions about what we're using tonight. Oh, you had more pictures. Go ahead.
Oh, I got a whole bunch of pictures.
Yeah, you can go flashing through those Saturn pictures. Muniba, we are using the Chabot 36-inch reflecting telescope. It's a classical Cassegrain telescope and a DSLR camera hooked up to it. And Backyard EOS is the software that we're using to display the images. And we're just have the camera in live view tonight because we're working with relatively bright objects. And related to that question is Jose's, who was mentioning that he has a DSLR infrared conversion camera. And I assume you mean that the infrared filter was removed from the DSLR. Those make excellent astrophotography cameras. They're not cooled, but they are much more sensitive in the red than off-the-shelf ones.
I'm looking for a animation that I have. I think I have it on this computer. Maybe not. Oh yeah, here we go.
Okay.
Oh God. I don't understand why this happens.
If you right click on it and hit open with, it'll open the proper application.
Yeah, you gotta use Windows Media Player, I think.
Yep. That's right. Okay.
There we go.
And then you gotta share it.
Yeah, yep. Bear with me a few minutes here, folks. Also, we are getting that's not it. Where is it?
Do a full desktop share.
Okay.
And then just bring it to the front. So look for the one that says desktop. I think it's the one in the upper left corner.
Okay,
I got it. There you
go. There we go.
All right.
All right. So this is made by the Cassini spacecraft as it orbited around Jupiter.
Saturn.
Yeah. I'm sorry. It orbited so that it crossed the plane of the rings. And so you'll see there goes a moon floating by. And there you see the edge on. They almost disappear. There'll be a couple of more moons that shows up. There's a faint one down there just below. And I think another one will come on by up in the top here in a second. So there's one right there. So it gives you a sense of how thin the rings are. It's only about 10 meters in most places and a maximum of about 100 meters. So the ring plane is pretty thin. So Richard, we're at 84% here.
I think we gotta call it quits then.
Call it a night as far as, we can keep talking and keep answering questions, but we are going to have to
We can do karaoke.
Yeah, there you go. So I am going to stop the tracking and stow the telescope.
Yep. All right.
And you guys can
I think we'll probably call it quits then. And we at least got a little bit of viewing in. Everyone should know. Go ahead, Gerald.
Let's make sure we catch all the questions.
One question was about the current year of Saturn. When does the current year of Saturn end? I'm not sure exactly what was meant by that. I think it had to do with
I think what whoever asked is getting at is how long is a Saturn year? And
30 Earth years, actually 29 and a half
okay,
Earth
got
years.
so I mean, it depends on where you're considering the starting point, but you should realize it takes it 29 years to orbit the sun.
Yeah, and I was just checking on Starry Night, and the next edge-on portion, or the next edge-on view of the rings, is going to be in between 2024 and 2025.
Oh, not too long.
No.
I'll try to hang around that long. So we're closing the roof, as you can see.
Yeah, I got to put
And
the,
here,
there we go. And all of a sudden, it's warmer in here.
I'm quite comfortable in my living room.
Yeah, I'll bet. I do want to mention before we sign off for tonight that you'll notice that we started at 9 o'clock tonight. Most everybody, I think, realized that, but some people came in at 9:30. We will be at 9 o'clock through fall, winter, and spring, and we won't go any earlier than that because it might conflict with other programs that the center and that the East Bay Astronomical Society may be putting on. So we'll stick to 9 o'clock. So tune in following Fridays at 9.
yeah.
And that'll do it. All right. Good night, everyone.
Good night,
Thanks for joining
everybody.
us.
Yeah, good night, everybody.